The next speaker is Dr. Krommer, who will be talking about analysis of non-local and nonlinear electromechanically coupled thin plates.
Okay, can you hear me? Well, I think so. Okay, thank you for the kind introduction. I'd like to say something about the topic. So if you throw out the word shells and nonlinear, we're talking about some piezoelectric plates. We had worked in the group of Hans Irschig, who gave the plenary lecture yesterday, while I was still in Linz for some time, and we also worked on problems concerned with vibration control, noise control. And then the people from this research center, which supports our work here, came up with the idea. They built a display, a haptic display with a response when you touch it, like a touch screen, where you get a little bit of a feeling that it has this kind of snap-through behavior. And they set it up, they built it, it worked really nice, and there was no trouble with it. But for me, coming from mechanics, I had one trouble with it. I was missing a little bit the rigor from a mechanics point of view, so I decided I'll look at the equations a little bit. So that's the outcome so far. In the future, we'd like to use this to optimize such a system. It's not the topic today. We haven't been there so far, and so I'm telling you what I wrote down and what I came up. So this is the outline. Maybe for those who are not familiar with it, I'll really shortly talk about the effect in a piezoelectric material that we're using here, then how we model these plates, a little bit about the stability and the nonlinear dynamics then, and a comparison of the simplified equations I'm using with some numerical solution, not making the same assumptions. Okay, these are the two effects I'm using here. It's the D31 and the D36, they're called. Just take a plate like this, put electrodes on the top, and then apply an electric potential difference. And what you get is, in the D31, an extension in two directions and a contraction in the thickness direction. If you use a D36 transducer, you just get this in-plane shear type of behavior. And then if you make biomorphs out of it, you get banding here or you get a torsion here. And you can do these problems. If the dimensions are like this, well, you can do a Bernoulli-Euler beam theory here, or you can do Sauvignon torsion here. But we'd like to go to plates, as like this display I tried to explain to you. It's a plate structure, so we have to go a little further. And in this case, what we do is, in the first step, we use some plane stress constitutive relations for both effects, D31, D36. They just look like this in a matrix notation, and if you go to a direct tensor notation, you can write it in this form. D, C, and EC are the thickness components of the electric displacement vector and of the electric field vector. And we have the stresses and the strains. And you get the D31 if you use this tensor E bar, and you just use the case where the deviatoric part of it is 0, and you get the D36 if the trace of this tensor is 0. So you have both effects included in this formulation. And then what I did is just use the von Karman equations. You have here the balance equations. These are the boundary conditions. And there's actually nothing in it other than the von Karman equations, some stiffness tensors, reference surface strain, and curvature tensor. And here's the actuation tensors. And in the actuation tensors, N bar and M bar, it's a layered structure here. Some layers are piezoelectric. Then you get the actuation in here through this tensor E and the thickness component of the electric field. And I remember yesterday, I don't know exactly who asked the question or made that comment. It was said it's important to also focus on the electrical part of a problem like this. I think it was you, yeah. So I have two more slides on the electrical part. Because EC, actually, I don't know the thickness component of the electric field. So we also use this charge equation of electrostatics here. And the electric field, which is defined as the negative gradient of the electric potential. We make an assumption that the in-plane part of the electric displacement vector in such a thin piezoelectric layer can be neglected compared to the out-of-plane, the thickness component. And then it turns out that this thickness component must be constant through the thickness of the layer, and we can integrate it and divide it by the thickness. and then recompute the electric field component in the thickness direction in this form. And you see now we have the known potential difference divided by the thickness and a term from some ECK in the cave layer. The bar here refers to this term, so this is kind of the direct piezoelectric effect that you see here in this formulation. That's fine as long as you know the electric potential difference. Final step in the electrical considerations is, what if we don't know the potential difference? Then we look at one layer like here. We have the electrodes on the top and the bottom. I'm using a hull over the electrode, and I'm computing the total charge by the Gauss law of electrostatics by this hull integral. And finally, you end up with a transducer equation which relates the charge to the voltage, and there is actually also this term from the mechanical strains. And if you have this, and V, for example, might not be known, say you have a sensor in an open circuit condition, then at least the current is 0 and the charge must be constant, so you can use this formulation then. This is just the summary of the result. Nothing changes in the balance equations, in the boundary conditions. The only change if you use these electrical considerations is that the stiffness tensors now have a part here and here where the piezoelectric tensors play a role. This is the coupling behavior. And nice thing is that the actuation tensors N bar and M bar now only depend on the electric voltage and not the electric field. So this is something you either know or you can relate to whatever happens in an electrical network, for example, that you connect to the layer by the transducer equation, which is written here. So this completes the formulation, and we can now, then I went to analyzing it for a specific case. There is a nice case in case if the lamination scheme is symmetric, then the strain energy decomposes additively into a membrane part and the bending part. And I assume further that all materials are transversely isotropic in each layer. And I studied a case that the edges of a polygonal plate are simply supported but immovable in the plane. In this case, there is an approximation known by the name of Berger, and he assumed that the second invariant of the reference surface strain tensor can be neglected compared to the square of the first invariant in the membrane strain energy, and then you find one simplified boundary value problem of fourth order for such a plate. What's interesting maybe here is the term MB, which is here, where you integrate over the whole, actually here the plate, because the electrode is all over the plate. If it would be only partially electroded, then over the domain of an electrode. So this is why the topic in the title mentioned non-local, because actually this is a non-local term, which is important in case the voltage is not known, because then you have to ensure the equipotential area condition at an electrode, and this is an integral formulation from the Gauss law of electrostatics with the Hull integration. So that's where this non-local formulation comes into the play, and I also have it with the parameter lowercase a here in this what is called a generalized Berger force here. Without lowercase a, this is just the Berger force as it is known from his original paper also, I think in '56. He published it in some, it was the Aerospace Engineering Journal, I think what is now the AIAA Journal. Okay, we analyze it by using a Ritz approximation in this form, and we use a Helmholtz eigenvalue problem with the same domain, which is written here as the solutions of it for the basis functions in the Ritz approximation. And with this, we end up with this nonlinear dynamical system. You can see, well, it's cubic nonlinearity here with the W square. It's a non-dimensional formulation. On the right-hand side, I have two terms, so to say. One is from the mechanical loading, and one is actually from the actuation, from the piezoelectric actuation. And on the left-hand side, the terms that have a beta here actually come from the non-local behavior. I will not really look at this today because I'm assuming the voltage to be known in all the results I'm showing you today and the analysis. So if you look at it in the static case, you can see if I have a one-term expansion for the right-hand side here, then, or not even only in the static case, then there is solutions where W1 is 0, and I'm using solutions where only one of all the other Wi's, the generalized coordinates, is non-zero. And it's written down here, so at the moment I'm not specifying which I I'm using. So these are the two equations I'm looking at. for the case of a one-term expansion for the right-hand side. It is possible that this equation also has the solution W1 is 0, in particular in the static, Wi in the static case, and for this test problem it's a piezo layer and the substrate layer, 1 times 1.5, it's 6 meters, it's 6 millimeters thick, and the voltage is applied at the piezoelectric layer. And for the case W, this should be an I. Wi is 0 other than for W1. I have this cubic equation, it's a catastrophe, it's shown here, with a slight difference that kappa 1 here, it depends on the mechanical part and also on the electrical part here, and therefore it relates to V, the voltage, which is also relates to N1, so N1 is the parameter that I'm using here, and this is why I have this non-symmetric behavior in these plots, as you see, for example, here in this one where the voltage, so to say, is changed, but for fixed mechanical loads, and here I'm changing the mechanical load for fixed voltages on these curves, and it's non-symmetric, as you can see here. Otherwise, this is just the result you get here. An interesting region is between these two curves which belong together and these two, so where kappa is 0 and kappa is 1, because if you look closer into it, you will find, well, this transcritical bifurcation at a certain value. For kappa p, in particular, these two curves belong together, and these two are for the same parameters, and if you go together with them, you will finally end up at this transcritical bifurcation, which you see also if you take a slice of this cusp here with this critical value kappa p1, then you have this type of behavior, which is shown here in detail. Now, this one-term solution is okay, but it doesn't really tell us where the stability where the loss of stability happens, because we should take into account one more equation here, like this one with an I. If you take only the bracketed term, which has to be 0 in case Wi is not 0 here, you get the equation of this ellipse in the W1, Wi plane, and you can see that n must be larger 0, which is the case in all these problems. And then you can use different i's for Wi here, and you see for W2, you get this behavior, and so you lose stability not here as in the one-term solution, but already here you have the snap buckling here. And you can also look at different i's. You see we have additional solutions here, but they are not very important because the Wi with I equals 2 is the most important one. And you can do it for all these curves that we have here, as long as Ni is larger than 0. So not for these three curves, it's only these two, and you see the behavior here. And this is a 3D plot of this behavior. You see, you're stable here, and then you have this ellipse in the W2, W1 plane, where you have the bifurcation at this point, and this is where you lose stability here. You can also look at these plots, maybe more, even a little bit more interesting if I vary n here, which is the actuation, and then you see that you have the stability, you have a stable branch here. Here stability is lost, and also here stability is lost, and this part is unstable. This is for the case of the kappa parameter larger than 0, or even actually larger than this transcritical one. For kappa smaller than this transcritical one, which would be curves these three and these three, which belong together, you have no more stable branches in this part of the plot here. Okay, and this is the 3D plot where you see stable, then you have the bifurcation into the second mode, W2, and the stable down here, and everything else here is unstable. And we can look at some imperfections for kappa 2, for example. These are the two 3D plots we just had. For kappa 2 is 0. With a small kappa 2, 0.02 with a minus, we still have this problem here. We have lost a loss of stability here, and also in this plot here and here. If kappa becomes larger, the imperfection, we don't have any unstable. Well, we have this unstable branch here and here, but this one is then just stable. Okay, the dynamics. We also looked at some, I would say we just looked at periodic solutions in case voltage is a constant voltage plus a time varying one, which is a harmonic function that we use here in time. And we have the forces here and also the voltage here in this part. So we have kind of a combination here between Duffing and Mathieu. And we just looked at periodic solution. I have to acknowledge here the work of Alois Steindl. He did these computations. I think the program's called MathCon. Okay. So we just use one frequency, and the red curve here is one of the curves we had before for the value of kappa p is negative. And now we just change the voltage a little bit, and you can see we have here non-stable resonance. And actually, this should be non-solid lines here, and this is the behavior we get if we look at this problem. In this problem, where we had this, actually, this is the ellipse that you can't see in this plot because you only see it in the 3D plot. With this type of behavior, we have some resonance here, then here it's unstable, everything here is unstable, and we have this one too. And we also looked at the third plot here, and this is the one, it's kind of red curve here is what we had before, stable, then you're going in the black curve, which is a mixed mode, so to say, with the second mode, and it's unstable to here, and then the red curve again, that's the static behavior, and in the dynamics we have here the resonance, we have one here, and we have actually, this should also be non-solid lines. This is the mixed mode, the pink one, which has unstable periodic solutions here. One thing I should say is that having only one term on the right side is not a very practical idea because, well, you have to have a loading that is like a sinus in this case, which is not the case. So if I have a constant loading like a pressure or so, I would at least take the fourth mode, which is the next symmetric mode. Then I have three equations to analyze. Two are non-homogeneous. These are just parameters, and for this simple case, you can see everything can be written in terms of one actuation force N0 and one force factor kappa P1, and I only need the Helmholtz eigenvalues of this plate, and then we can analyze. And this time you use this second equation here, and the bracketed term now, it's not an ellipse, it's an ellipsoid now, which you can use and plug in the solution here for W0 non-zero in these bracketed terms, and for this case you get these two equations which are linear. They're actually planes in the W1, W4, kappa and n plane, and they have one intersecting line, and this intersecting line of these two plates actually also intersects the equilibrium branches. The red curve here is this line, which is not a branch of equilibrium, but it's just the connection between where actually we lost stability here and in this plot. And we did this also because with this three-term solution, we can also compare to finite elements in a plate solution or in a shell solution. And what we use is another work we did on shells, nonlinear shells. Basically, the shell is a material surface in two configurations, undeformed, the reference configuration, and the deformed configuration. In each configuration, we work with position, tangential plane, the base vectors in the tangential plane, the normal vector, some differential operator, first, second metric, and the elementary area. We use the two configurations. The shell itself, then, as it is not just a surface, other points are just pinned to the normal vector, so to say, with a constant distance from this surface, so it's kind of a Kirchhoff approximation here. We make no other approximations from a geometrical point of view. Introduce some strain tensors here related to the first and second metric and to the deformation gradient. Then we do some numerical modeling by using the enthalpy that we would have in the linear theory of a plate, replacing the strain measures there with the nonlinear strain measures, and then just seeking for an extremum. The minimum is not correct here. It's not necessarily a minimum for an extremum. We use these finite elements in the shell theory, and now we can compare our simple three-term solution that we had before with these finite elements, and you can see for no voltage we have a very good result, which is actually also the case because 0.005 is 5 millimeters and the plate is 6 millimeters thick, so we're in the range of the thickness of the plate. This one is then for a non-zero voltage, and you can see we still have a good result between finite elements, and the finite elements have nothing like a von Karman approximation or a Berger approximation. They have actually no other approximation than the fact that the points remain on the normal to the surface that we're using to describe the behavior. So this is a nice result, but you can see not so good as here because we're reaching like 10 millimeters, which is not so good. Anyway, we also did these computations by changing, leaving the force fixed and varying the electric voltage. So for no force, we have this behavior again. We have a deviation here when we go beyond the thickness of the plate. And also here, we get this interesting behavior that if the voltage is increased, we lose stability here and we go to and we snap buckle to the other side here at a different value than in the analytical solution, but this is already twice the thickness of the plate, so that is to be expected. And with this, I'd like to shortly conclude. I did this because I was interested in such plates where the people did those, they used something to make it automatically snap through, and I wanted to see how we can do that in the future to optimize it. So we need some equations, and we think we can do something with it. Also, I wanted to do some electrostatics. I didn't have the time to do that. And maybe, as a last comment, and then I'm done, the equations you saw here are actually what Hans Jirsig used in his second example yesterday for a beam. It's just for the plate, and we could use it to do some shape control with it. And I wanted to say one last thing, which I don't remember. So I'm coming to the very last thing. Thank you so much for your kind attention, and please feel free to ask whatever you want to ask.
Okay, thank you. Any questions, comments?
When you compare your results to the finite element approximation, are you using a commercial code?
No.
A code made by yourself? My guess is if you use a commercial code, you will find a completely different results because of the numerical damping that is inserted automatically in the commercial code.
So far, we have not tried these results, but we have tried our code for the nonlinear shells and compared it to like Abacus using 3D elements there, in particular for plates, not so much for shells, but also there, and we get good results. So we believe that as long as the thickness of the shell or the plate we're modeling with our code is within the eligible range, we get good results compared to Abacus. Actually, that has not been a problem. I think we would get it here too.
Please.
I believe the problem of a shell with piezoelectric actuation can be interesting for energy harvesting because the snap through motion and so on. I'm wondering if you thought about it. B, slide number 12, you talked about transcritical bifurcation.
Yeah.
If you don't mind explaining to me exactly what is the stable and what is the unstable and so on. I got lost, honestly, what's going on.
Yep. Well, this is, you're starting somewhere here, you're increasing the voltage, so to say, then the parameter n becomes larger. You're reaching this point where you have a bifurcation, it's a transcritical one into a stable branch here, and these two unstable ones here. You could find exactly this behavior in the simplest case if you have a beam, a rigid beam, which is simply supported at the bottom. You're having it here, and you're using a spring that is supported to the side. Then you get this type of behavior locally where this bifurcation occurs. So it's because of the non-symmetry. That's the simplest example that you can think of, that you can just implement easily. So this is the bar, it's rigid, and there is the spring going sideways. And there you get this behavior.
Very much enjoy your rigor.
Good point.
The comment we always show that the good agreement. Did you find places in your parameter space when the agreement is not that good?
That's a good question, and it's a very fair question because I would maybe ask it myself. This is what we looked at so far, to be very honest.
Yeah.
And it's cases that are also, to be very honest with you, far beyond where you could even go. So it is already at a critical case in the sense of the equations itself that I'm using. So it's not something where there is no trouble due to geometric nonlinearity or something.
What I'm interested in, when you have basically verge of stability, let's say coexisting with attractors, then some of these agreements could be
now, concerning your question, some of these agreements, I do not disagree with you, but I would have to look in more detail at the parameters and so on. We didn't really not do that at the moment.
Thank you.
You're welcome. Thank you.